Beneath more than a mile and a half of solid ice, in a place no human being has ever set foot or laid eyes on directly, scientists just found more than 200 volcanoes. Not a handful, not a dozen. 207 separate volcanic structures, hidden the entire time beneath one of the most remote, least understood landscapes on the planet, mapped for the first time only because retreating ice and improving technology finally gave researchers the tools to actually see what's been sitting down there. And that's only one piece of what's coming into view as Antarctica's ice sheet changes. Scientists have also just uncovered an entire buried geological structure the size of a small country, evidence of ancient tectonic violence connected to the breakup of Earth's most famous lost supercontinent. Today we're breaking down exactly what's emerging from beneath Antarctica's ice, why melting and modern technology are finally revealing it, and why some of what scientists are finding down there might actually make the continent's future considerably more unpredictable than anyone previously understood. Here's what makes this moment in Antarctic science genuinely unlike anything that's come before it. For most of human history, the interior of this continent was effectively a black box, a featureless white expanse on every map, its actual bedrock geology, its buried mountains and basins and volcanoes, completely inaccessible to direct observation. That's changing now, and it's changing fast. Not because anyone finally walked out there with a shovel, but because the exact same forces reshaping the ice sheet's future are simultaneously giving scientists their first real look at what's been hiding beneath it the entire time. Let's start with the volcanoes, because the sheer number alone is enough to reshape how you think about what's actually sitting beneath the Antarctic ice sheet. In February 2026, an international team of researchers published the first continent-wide inventory of Antarctica's hidden volcanic structures in the journal Earth Science Reviews. Compiling data from radar surveys, satellite imagery, and decades of accumulated volcanic records into a single, comprehensive catalog, researchers named ANT-SGV-25. What they documented was genuinely staggering in scope. 207 separate subglacial volcanic structures. Buried beneath Antarctica's ice sheet, the overwhelming majority of them clustered specifically in West Antarctica, the exact region of the continent that's currently experiencing the most severe and rapid ice loss anywhere on the ice sheet. Lead researcher Kui Shangbin explained the significance directly, noting that these hidden volcanoes can alter the shape of the landscape sitting beneath the ice, encourage melting directly at the base of the ice sheet, regulate how meltwater moves and drains underground, and ultimately influence how the ice itself flows and how stable the entire ice sheet actually is. It's worth understanding how researchers actually managed to compile a catalog this comprehensive, given that virtually none of these 207 structures are visible from the surface in any conventional sense. The team behind the ANT-SGV-25 inventory combined several genuinely distinct data sources, ice-penetrating radar capable of detecting the telltale conical shapes and structural signatures. Volcanoes typically leave in the rock and ice layers above them. Satellite gravity and magnetic measurements sensitive enough to pick up the subtle density differences volcanic rock produces compared to the surrounding bedrock, and decades of scattered, previously uncoordinated volcanic records collected by individual research expeditions over the better part of a century. Bringing all of that fragmented data together into one unified continent-wide inventory for the first time is precisely what allowed researchers to recognize the full scale of Antarctica's hidden volcanic landscape, rather than the scattered, incomplete picture that had existed in the scientific literature beforehand. It's also worth noting that this isn't a fully confirmed count in the strictest sense. Researchers describe these as candidate or probable volcanic structures based on the available remote sensing evidence, with ongoing and future fieldwork needed to fully confirm the volcanic origin of every individual site included in the catalog. To understand why a volcano buried beneath a mile or more of solid ice actually matters for how that ice behaves, you need to picture the fundamentally different way heat operates at the base of an ice sheet compared to how you'd normally think about a volcano. These aren't necessarily volcanoes capable of a dramatic, ash-spewing eruption breaking through the surface anytime soon. Their influence is quieter, and in some ways more insidious, radiating geothermal heat continuously upward into the ice, sitting directly above them, gradually warming the base of the ice sheet from below in a way that satellite observations of the surface would never directly reveal. Ice, sitting on top of relatively warm, geologically active bedrock, behaves very differently from ice sitting on cold, stable rock, becoming more prone to basal melting, more capable of sliding rather than staying frozen firmly in place, and ultimately more likely to flow toward the ocean at an accelerated pace. Mapping exactly where these 207 volcanic structures sit and how large and active each one actually is gives researchers genuinely critical information for building far more accurate models of how quickly specific sections of the West Antarctic ice sheet might actually be capable of destabilizing. This finding connects directly to a specific piece of Antarctic ice that already carries an ominous nickname in scientific circles, and understanding that connection helps explain why this volcanic inventory matters so much right now. Thwaites Glacier, widely known as the Doomsday Glacier because of its outsized potential contribution to future sea level rise, has already been the subject of research documenting significant geothermal heat flowing up from beneath the ice stream itself. Ice losses from Thwaites alone are currently responsible for roughly 4% of all global sea level rise, and researchers have specifically flagged concern that this figure could climb further. Since virtually no other major ice stream on the planet has this particular combination of vulnerabilities working against it simultaneously. Understanding the broader volcanic landscape hidden beneath West Antarctica, the same region where Thwaites sits, gives scientists crucial additional context for exactly why this specific glacier behaves the way it does, and for identifying whether other, less closely studied glaciers nearby might be sitting on top of similarly concerning geological hotspots that haven't yet drawn the same level of dedicated research attention. It's worth grounding this discovery against something Antarctica has already made undeniably visible, because the continent isn't purely a landscape of hidden, buried volcanic activity. Mount Erebus, rising from Ross Island, is one of the most active volcanoes on Earth and the southernmost currently erupting volcano on the planet. Its summit crater holding a rare, persistent lava lake that's remained active for decades in full view of researchers stationed nearby. Erebus stands as living proof that Antarctica's volcanic activity isn't purely a historical curiosity confined to structures buried under ice, but includes genuinely active systems capable of continuous, observable behavior even in the most extreme conditions on the planet. Placing the newly cataloged 207 subglacial structures alongside a confirmed, actively erupting volcano like Erebus gives researchers a genuinely useful reference point for understanding just how volcanically alive this continent actually remains beneath its icy surface. Now, let's turn to the second genuinely mind-blowing discovery, because this one reaches back not just decades or centuries, but across more than 100 million years of Earth's deep geological history. In June 2026, researchers published findings in the journal Nature Geoscience describing an enormous, previously unrecognized geological structure buried beneath East Antarctica, a discovery that fundamentally reshapes how scientists understand the deep architecture of the entire continent. Using radar data capable of seeing through ice exceeding 3 kilometers, nearly 2 miles in thickness in some locations, researchers identified a vast fan-shaped network of interconnected basins stretching across a huge portion of East Antarctica, revealing that several individual geological features scientists had previously studied and mapped as separate, unrelated structures were actually all connected pieces of one single massive underlying formation. Researchers have named this newly recognized structure the East Antarctic Fault Basin Province, and its sheer scale places it among the largest tectonic features ever documented anywhere on the planet. The story behind how this structure actually formed reaches back to one of the most consequential geological events in the planet's history, the gradual breakup of the ancient supercontinent Gondwana. Scientists studying the newly mapped basin network believe it developed through multiple distinct tectonic episodes tied directly to that breakup process, as the landmass that would eventually become Antarctica slowly tore away from the other continents that once surrounded it. The structure may also be directly connected to the later, separate geological event that finally split Antarctica away from Australia, and researchers suspect it could have played a genuine role in shaping exactly how and where that continental separation ultimately occurred. In other words, buried beneath nearly 2 miles of ice sits a fossilized record of one of the most dramatic chapters in the entire planet's tectonic history, a scar from the slow-motion violence of continents tearing themselves apart, hidden from view for tens of millions of years, until modern radar technology finally became sensitive enough to trace its full extent. It's worth understanding just how deep the origins of this newly mapped basin network actually reach, because the timeline involved is genuinely difficult to fully absorb. Researchers believe the structure began forming when Antarctica and Africa first started pulling apart during the Jurassic period, somewhere between 201 and 143 million years ago, part of the broader, slow-motion breakup of Gondwana that eventually scattered the continents into the arrangement we recognize today. Separate research published in the journal Science in 2026 has connected this same deep tectonic history to an entirely different, equally consequential outcome, showing that the gradual uplift of East Antarctica's mountainous interior, driven by a phenomenon researchers call mantle waves rippling beneath the continent, as it broke away from its neighbors, created exactly the kind of elevated terrain needed for snow and ice to first begin accumulating there roughly 34 million years ago. In other words, the same deep continental rifting responsible for carving out this newly discovered basin network also appears connected to the very reason Antarctica became capable of hosting a massive ice sheet in the first place, A genuinely remarkable thread connecting the continent's ancient tectonic violence directly to its modern identity as the coldest, iciest place on the planet. This discovery matters for genuinely practical reasons too, well beyond its value as a window into deep geological history. The physical structure of the bedrock sitting beneath an ice sheet has a direct, measurable influence on how that ice actually behaves as it flows toward the coast. Ancient fault lines and basin structures, like the ones mapped in this newly identified province, can create channels and pathways that influence exactly where ice moves fastest, where meltwater collects and drains, and how vulnerable specific sections of the ice sheet might be to destabilization as warming conditions continue reshaping the broader Antarctic environment. Researchers studying this newly identified structure have specifically noted that understanding it could meaningfully improve scientists' ability to predict how the East Antarctic ice sheet, the single largest ice sheet on the entire planet, storing enough frozen water to raise global sea levels by roughly 52 meters if it were ever to fully melt, is actually likely to respond to continued warming in the decades ahead. Here's the part of this story that ties both of these discoveries together, and it's genuinely worth understanding, because it explains why so much of what's currently emerging from beneath Antarctica's ice is being documented right now in this specific window of scientific history, rather than decades earlier or decades from now. Antarctica's ice sheet isn't simply melting from the top down, the way most people intuitively picture climate-driven ice loss happening. Researchers studying the continent have increasingly focused on a genuinely more alarming mechanism: warm ocean water working its way beneath floating ice shelves and melting the ice from underneath out of direct view of any satellite camera. A study published in 2026 found that long, channel-like structures carved into the underside of these ice shelves can actually trap warmer ocean water once it arrives, holding it in place longer than it would otherwise linger and dramatically accelerating melting from below. A process researchers warned current climate models may be missing entirely. Separate research, led by Scripps Institution of Oceanography scientist Sarah Perkey, used 40 years of reconstructed ocean data to document the steady, measurable advance of a warm water mass called circumpolar deep water toward the Antarctic coastline, describing the shift in genuinely vivid terms, as though someone had turned on a hot tap, and the entire bath surrounding the continent was gradually warming as a result. A separate 2026 study published in Nature Communications, focused specifically on Antarctica's Fimbul ice shelf, reinforced the same underlying picture from yet another angle, finding that even small temperature differences in the surrounding ocean water can trigger dramatically outsized melting once that warmer water becomes trapped inside the channelized topography carved into the base of the ice. Researchers behind that study cautioned directly against underestimating these compounding dynamics, warning that if ice shelves like Fimbul continue weakening from this kind of hidden, channel-driven melting, the glaciers they currently help hold back could begin flowing into the ocean considerably faster than existing projections account for. That combination, ice thinning and retreating from below as warmer water reaches further beneath it, is precisely why researchers now have unprecedented access to data about what's actually sitting underneath the ice sheet. Thinning ice allows radar and other remote sensing technology to see through it with considerably more clarity and precision than was possible when the ice sat thicker and more stable. Increased scientific attention and funding, driven directly by growing concern about how quickly Antarctica's ice might actually be capable of destabilizing, has funded exactly the kind of large-scale, continent-spanning survey work that produced both the volcanic inventory and the newly mapped basin network. In a genuinely direct sense, the same warming trends threatening to destabilize Antarctica's ice are also the reason scientists finally have the tools and the motivation to map, in unprecedented detail, exactly what's been hiding beneath that ice the entire time. It's worth understanding that these two discoveries don't sit in isolation from each other or from the broader body of research, reshaping scientists' understanding of Antarctica's vulnerability more generally. A separate 2026 study led by University of Maryland researcher Madeline Youngs, published in Nature Geoscience, identified what researchers describe as a hidden accelerant in the overall ice loss process, a self-reinforcing feedback loop where melting ice actually changes broader ocean circulation patterns, and those changed circulation patterns in turn influence how much additional ice subsequently melts. Youngs was direct about a genuinely significant gap in current climate policy, noting that most of the climate models actually informing international decision-making, including those used by the Intergovernmental Panel on Climate Change, treat ice melt as a simple, fixed input rather than an interactive process capable of feeding back on itself in exactly this way. Her research suggests this overlooked feedback loop may be contributing to sea level rise on a scale comparable to the direct effects of a warming atmosphere alone, a genuinely significant revision to how scientists need to think about Antarctica's overall trajectory going forward. There's also genuinely compelling evidence from Antarctica's own deep past suggesting exactly how quickly this kind of compounding, self-reinforcing process can actually unfold once it gets started. Research published in Nature Geoscience and led by Professor Yusuke Suganuma of Japan's National Institute of Polar Research examined a dramatic retreat that struck East Antarctica roughly 9,000 years ago, finding that warm, deep ocean water surging beneath the region's floating ice shelves triggered their collapse, which then set off what researchers termed a cascading positive feedback, with melting in one specific area accelerating melting in entirely separate regions through interconnected ocean currents circling the continent. Researchers studying this ancient event have been explicit that the same basic mechanism could genuinely be reawakening today, as warmer water continues creeping beneath modern glaciers around the continent, a sobering historical precedent for exactly how fast a seemingly stable ice sheet can actually begin to fall apart, once the right combination of oceanic conditions falls into place. It's genuinely worth noting that not every surprising Antarctic discovery emerging from this current wave of research points toward a more dangerous outlook. And being fair to the full body of evidence means acknowledging that too. Research from Rutgers University, published in early 2026, examined a long-standing theory that melting Antarctic glaciers would release enough iron into the surrounding ocean to spark algae blooms capable of pulling meaningful amounts of carbon dioxide out of the atmosphere. A genuinely hopeful idea that had offered one of the few potential silver linings in an otherwise troubling body of Antarctic climate research. New field data from West Antarctica complicated that hope considerably, finding that meltwater actually delivers far less usable iron than scientists had previously assumed, with most of the iron reaching the Southern Ocean, instead coming from deep water and seafloor sediments in a chemical form marine algae can't easily use. That finding doesn't make Antarctica's situation more dangerous on its own, but it does illustrate the genuinely two-sided nature of what's currently being discovered, some of it revealing new risks, some of it closing off previously hoped-for sources of relief, all of it adding up to a considerably more complete and considerably more complicated picture than scientists had access to even a few years ago. Even Antarctica's sea ice, the frozen ocean surface surrounding the continent rather than the massive ice sheet sitting on land, has revealed its own genuinely startling story over the past year of research. For decades, Antarctic sea ice actually defied the broader pattern of global warming, slowly expanding even as Arctic sea ice steadily declined, until 2015, when that trend abruptly, dramatically reversed. A study published in May 2026 and led by researchers at the University of Southampton finally identified exactly why, describing what they called a triple whammy of compounding climate factors. Unusually powerful winds in the Southern Ocean dragged warm, salty deep water up toward the surface. That surfacing heat triggered rapid melting, and by around 2018, the entire system had become trapped in a self-perpetuating feedback loop with less remaining sea ice, meaning the ocean surface stayed warmer and saltier, which in turn made it considerably harder for meaningful new ice to reform. Lead researcher Aditya Narayanan described the result bluntly, noting the process wiped out an area of sea ice roughly equivalent to the entire landmass of Greenland, contributing directly to the record-breaking lows Antarctic sea ice has registered in recent years. So what should you actually take away from this rapidly expanding picture of what's hiding beneath and surrounding Antarctica's ice? The honest answer is that scientists are living through a genuinely unprecedented window of discovery, one where retreating ice, advancing technology, and intensifying research investment are combining to reveal details about this continent's deep structure and history that remained completely invisible to humanity for the entirety of recorded civilization. 207 hidden volcanoes, an ancient tectonic scar the size of a small country, connected to the literal breakup of a lost supercontinent, warm water creeping beneath the ice from below in ways current climate models may still be underestimating. Each of these discoveries is genuinely remarkable purely as a piece of scientific knowledge, a window into processes, and landscapes that have sat hidden and unstudied for millions of years. But each one also carries genuine practical weight for understanding exactly how Antarctica's ice sheet, the single largest reservoir of frozen fresh water anywhere on the planet, is actually likely to behave as the surrounding ocean and atmosphere continue warming in the years ahead. That's the real story behind what's currently emerging from beneath Antarctica's ice, a continent-sized landscape of hidden volcanoes, ancient fault systems, and warming ocean currents, all coming into scientific view at almost exactly the same moment that researchers most urgently need to understand them. Scientists continue mapping this hidden world in ever greater detail, expanding radar surveys, deploying new generations of ocean-sensing floats, and building increasingly sophisticated models that finally account for the kind of interconnected feedback loops earlier research overlooked entirely. Stay with this channel because we'll keep tracking every new discovery emerging from this remarkable, still largely unmapped corner of the planet. And this is exactly the kind of story where what scientists find next could genuinely reshape how the rest of the world needs to think about the ocean's future.